last class we saw something about voltage regulators, how important parameters like line regulation, load regulation, temperature coefficient of V naught. Now, this is something that I did not mention, but however, this is also equally important. Okay, temperature coefficient of V naught. Obviously, temperature coefficient of V naught is dependent upon temperature coefficient of V ref, and that we have already made it to be equal to 0. So, we are not so much bothered about that factor in the design. Already IC designer has made it very close to 0. What he wants you to do is must select the resistors properly externally, so that V reference into 1 plus R2 over R1 will be the output voltage, and therefore, R2 and R1 should not disturb the already low temperature coefficient of your output voltage. Okay. Ripple rejection is something that we have seen. Output impedance, its importance also we have understood in the last class. That is why I am not putting it as output resistance, but insisting that you should evaluate the output impedance. Okay. That should be kept very low. Now, today's class we will understand something about the limitations. Okay. What are the limiting factors in the design? This is an important aspect. There is no point in knowing about these parameters exactly and not knowing about the limitations. And this is something that commonly happens. Okay. You have designed your circuit properly, but because of your ignorance about your limitations, you find that the circuit is not functioning. Okay. So, limitations are very important, okay, and these have to be understood by the designer. Let us therefore first see the most important factor in the voltage regulator. Obviously, it is designed to give a certain voltage which is independent of the input voltage variation. That is, line regulation should be good and load regulation should be good. That means, even when I demand from it various ranges of current, it should have output voltage remaining constant. These are the two important factors. That means, first limitations that we have to consider are the limitations on Vi and limitations on I naught. Okay. So, let us see this, how these limitations come about. Okay. Then question is there a limitation on V naught that you can get? Actually, there is another limitation which is called Vi minus V naught limitation. Okay. Then very important limitation on this, that is PD, power dissipation of the IC. So, we have to understand all these limitations, okay, thoroughly. If we are going to design an IC, then we have to understand how these limitations come about, each of these. Consequent to this particular limitation, which is directly coming in terms of what is called an important parameter associated with the voltage regulator, which is called obviously efficiency. What is efficiency? That is well known. Okay. It is nothing but output power divided by input power. Okay. Tells you how efficient you have been as a designer of this IC.
Is it related to power dissipation?
Yeah, it is primarily related to what is the idea of this efficiency. Actually, we do not want the regulator to be used at all. When we are designing a separate system, voltage regulator is an accessory. Why does it become necessary? Because if we directly use this voltage, our operating points and all will keep shifting, and we have to make our design more complicated. Okay. So, we would like this voltage regulator to give us a supply which is relatively independent of the input voltage. So, this has been inserted in between your system, okay, and the input power. But in this process, you should not spend lot of power in the IC itself. Okay. That is an inefficient way of doing it. This particular thing is going to be introduced in such a manner that in spite of introduction of this, right, you are using the power efficiently. That means what this IC should dissipate should be very low compared to what you are using, okay, from it. That means efficiency of any regulator should be good. That means it should be as close to 100% as possible. Okay. So, what is it that prevents you from getting it close to 100% efficiency? Okay. This is something that the designer has to investigate. Okay. So, that is an important parameter associated with the regulator. Consequently, what are the limitations on the efficiency? Right? Is that clear? So, let us now discuss. First, let us take it this way. We will go this way, because this is finally the most important thing. The voltage regulator is not doing any amplification or anything. It is just being inserted into the power scheme, DC power, okay, so that output DC power, okay, is something that we get anyway, okay, with an output voltage which is constant. So, obviously, we know that V naught is going to be V reference into, in that particular design, 1 plus R2 over R1. This portion of the circuit is something that you have designed, the user has designed. If it is a 5-terminal regulator, these components I have to put externally, okay, to get the required regulated output voltage. If it is a 3-terminal regulator, even this is incorporated within the IC, okay, so you get a fixed regulated output voltage. So, load is anyway something that is connected to it. This load may be varying with time. I mean, we are not sure what it is going to be, because it may be not just a resistance, it is some system and subsystem connected to this, right. And these subsystems in turn may be drawing power depending upon how they are acting on the signal. Okay. So, this is a varying load. Now, I am putting R1 and R2 to the inverting terminal in this fashion, so that V naught into R1 by R1 plus R2 is what is compared with V reference, which is here. Okay. So, V reference, if the loop gain is very high, V reference is very nearly equal to V naught into R1 by R1 plus R2, or in turn we know that V naught is equal to V reference into 1 plus R2 over R. This is an important design equation. So, now the question is, given V naught, because you are going to design it for a certain V naught and a varying value of I naught from I naught minimum to I naught maximum. This is the design thing, right. So, V naught is given to you, and I naught is going to change from I naught minimum to I naught maximum. Okay. In such a situation, we are having already limitation on V in. V in may be changing from V in minimum to V in maximum. Now, does this circuit work satisfactorily, okay, when V in changes from V in minimum to V in maximum, when I naught in turn changes from I naught minimum to I naught maximum. Okay. So, this is something that we have to investigate. That is what we are going to do now. Okay. Now, let us see, when we are having V naught as the output voltage and I naught is the current drawn, okay, there is going to be some amount of current drawn from this also. Obviously, this current is going to be made much less than this current, because this is in my hand. Okay. But you should not make it too small, okay, in order to make sure that the voltage here is R1 by R1 plus R2, this current should be negligibly small compared to this. So, there is a maximum limitation on R1 plus R2, okay, as well as minimum value for R1 plus R2. So, R1 plus R2 should not be made too low, okay, lest this current becomes comparable to this current. So, this current should be very small compared to the load current. That is how a designer should design. Okay. This is only for sampling the output voltage, and this current should not be made too small, because otherwise you cannot now assume V naught into R1 by R1 plus R2 as the voltage here. That you should be let it become, because unless that becomes the voltage here, we cannot then equate it to V reference, right. So, that means if this current becomes comparable to this current, there is a dependence on active parameters on output voltage, which we do not want. Okay. So, these are designed properly. If you assume, then this current is going to be predominantly the output current. Okay. Forget about this now for the time being. So, this output current is flowing through this, and it is essentially flowing through this, and that is going to be the dominant input current. Input current now will comprise, okay, of this current plus the various bias currents, these are, okay, of the IC. So, input current is normally going to be output current plus the various bias current drawn from this. And input current in a good circuit, input current has to be very close to output current in a good circuit, efficient circuit, okay, because for biasing these things you should take as low a current as possible. Is that clear? So, essentially in a regulator we are going to have this consideration, I is going to be I naught plus the various bias current required, and this has to be made very small, so that this is very nearly equal to I naught. Is this clear? Under that situation, what is the efficiency? Efficiency is given as V naught into I naught by V I into I I, and we have just now said I I is normally very close to I naught. So, particularly we are discussing efficiency when it is delivering lot of power, but here it means when it is for a fixed voltage you are designing, it means it is delivering maximum current. Okay. That situation obviously I naught is very close to I I, and therefore, efficiency is in a good regulator ratio of output voltage to input voltage. This is important to understand. Okay. So, what does it mean? This is nothing but, okay, V naught divided by, okay, V naught plus V I minus V naught. Okay. What is important is that V I minus V naught should be made very, very small in a good design. This is what is called a differential voltage. This differential voltage is important in the case of voltage regulators, and it is given as Vi minus V naught differential. That there is a minimum. You cannot make it lower than a certain value. So, what is that limitation? Let us look at the circuit now. Okay. That limitation on Vi minus V naught minimum, this has to be made very low, that we understood. Okay. So, can it be made as small as we please? No. Given a circuit, we can find out what this minimum is going to be. Let us see that. This is V naught. We come through this and come to the circuit here. We have here V gamma. Okay. 1 V gamma. Okay. Then we come to this. This is connected to this. This potential can swing and come close to this under the limitation. So, this can be 0. Right. So, if this can be 0, there is one more V gamma. So, you have 2 V gamma. Whatever you do, it cannot be made less than 2 V gamma for this circuit. Now, if you put a Darlington pair here, it will become 3 V gamma. If in order to increase the power capability of the transistor IC, right, regulator, you put more and more of this pyramid like structure, accordingly the V naught minus Vi differential will increase. Okay. So, for example, in the case of 3085, how many such transistors are there? You can quickly look at the circuit, or 723, you can quickly look at the circuit and for yourself find out what will be the V naught minus Vi minimum that can be had in a given circuit. Have you understood this? Is it clear? So, collector to base voltage, the limitation is that it can be made as small as 0 volts. Given that, the rest of it is due to the V gammas. In this circuit, it is 2 V gamma. Okay. So, that is one limitation. Is this understood? That is coming, okay, because we want to make the efficiency as close to 1 as possible. Okay. In the process, we are having this problem of not being able to make it less than a certain value. Okay. Now, is there a maximum? Yes. What happens is, let us consider the power dissipated in the IC. What is the power dissipated in the IC? Vi II minus V naught I naught, and we said this is very close to, okay, Vi minus V naught into I naught. When power dissipated in the IC is maximum, when will it become maximum? When I naught is maximum, okay, and Vi minus V naught is maximum. That means PD max occurs in one case, right? This is one way, occurs when Vi minus V naught is maximum, I naught is maximum. Is this clear? So, given PD max for the IC, manufacturer will tell you this IC is capable of dissipating only this much power. Okay. Then given PD max, okay, you can and knowing I naught max, okay, you are able to find out Vi minus V naught maximum that you can have. If V naught is already fixed as equal to V reference into 1 plus R2 over R1, then this will give you a limitation on Vi max. One limitation on Vi max going through this procedure of power dissipation. This does not mean that this is going to be the final thing. Okay. So, one limitation on V I max can be obtained from P D max. That comes primarily because of V I minus V naught max. Is it clear on that? Now, if both V I is, V I are made, V I and V naught are made variable, in the sense V I is varying anyway, we know, from V I minimum to V I maximum. V naught I want to keep varying, it is a varying regulated power supply I want to do. In that situation, obviously you have to consider here V I max minus V naught min into I naught max. Is this clear? And that should be the V I max to which your circuit should be limited. Okay. Now, is there any other problem connected with this? Is I naught minimum causing any problem? That should there be a minimum I naught, or will it stop working if I do not draw any load? These are things which you have to answer. Anyway, there is a bleeder resistance here. Okay? This current is going to be drawn from the circuit in any case, and as long as it is being drawn, if the circuit is still functional, okay, there is no problem. So, that is not normally any problem for you. Okay? So, I naught has a limitation on this, that I naught max is something that can come about from, okay, P D max also, right. If it is not given, and you know the variation of V I from V I minimum to V I max, then you can get a limitation on I naught max from the circuit. Okay? That is based on power dissipation. Now, there are variety of things here. You should understand this circuit thoroughly when you are a designer. If this is I naught and this is some I R, okay, current going here, this current is going to be I naught plus I R, okay, and this current is going to be I naught plus I R divided by beta plus 1. You put it as beta plus 1 because this is going to be a power transistor. I mean, ultimately maybe you are putting, in order to improve the power dissipation capability of the transistor, you might put, okay, this Darlington pair of transistors. So, betas need not be very high for those. So, if you are putting Darlington pair, do not take beta as effective beta as beta 1, beta squared or beta cubed or something. It will be beta 1 into beta 2 into beta 3. Okay. So, this is the base current that is given, and therefore, you have this particular thing that this current is going into this, and this is a current source current going. Okay. Now, there is a constant current drawn from this I naught. How does this work? This current is going to be, let us say, either it is going to be decreasing, okay, or it is going to increase. Okay. Now, let us say I naught minus delta I, and this will be I naught plus delta I, okay, depending upon the control scheme, right, depending upon how much you are demanding here. So, I naught by 2, and this is I naught by 2 plus delta I. Okay. Around quiescent, whatever be the quiescent, we do not know what it is, right, it is going to be I naught by 2. Okay. Then we have I naught by 2 minus delta I. That means it is going to be deprived of current. Where is the current going? This is demanding current here, right. How is it demanding current? You are loading it more and more. when this is getting loaded more and more, this current has to come from here. Okay. Where is it coming from? It has to come from this constant current source. Originally this was I naught by 2 and this was I naught by 2. This was giving very nearly 0 current. That's what is necessary to sustain the biasing here. Okay. Now, as the current demand here increases, this is going to increase and this current is going to decrease. Ultimately, what will happen? This can go to 0. That means most of the current is going to be demanded by this, right. That means this current, which is, what is the current value here, right, I naught itself, right, because by that time this transistor is going to be deprived of all current and this current is going to be drawn by this I naught, and therefore this I naught is going to be pumped into this. So, I naught is going to pump it into this, therefore the maximum current that you can have is I naught into beta plus 1. This is the maximum current that this circuit is capable of giving with this differential amplifier functioning satisfactorily. Have you understood this? So, that is the only available current to you, and that is another limitation, right. If you demand more current than that, this circuit will no longer act as a regulator, right. This is another, this is not coming from what? Any power consideration. This is independent of the power consideration. What I have done is kept, okay, V naught here and kept varied this load so that the current demanded is more and more. What might happen is power dissipated may be still very small because Vi is kept very close to V naught, let us say. So, I am getting therefore another value for I naught max. Have you understood this? From circuit operational viewpoint, okay, you are getting another value for I naught max. You have to see now. We have already got 2 values for I naught max. The lower one will prevail ultimately. Is clear? One limitation. This is something again which is not really seen by the user, right. When he is using it, he might just wonder why the circuit is not functioning in spite of the fact that his power dissipation etc. is perfectly all right. Okay. So, this is one thing.
So, if we put another emitter follower, this might be
true. I mean, the way to do it is simply telling you that do not load me more, I am not capable of giving you that current, right. So, you put a current amplifier, that means the solution comes in the form of another transistor being connected in Darlington mode of, right. So, that will reduce the demand on this, and for that load it will function. This way therefore, you can go on doing it until obviously the transistor says that is my maximum current of operation now. Okay. There is a maximum current of operation for the transistor itself. Okay. Do you understand that? So, the third limitation now, I naught max can occur simply because the transistor says that current cannot be passed through it. Okay. I naught max. Transistors themselves will have maximum current of operation, maximum voltage that can occur as reverse bias voltage between collector and base, and maximum power dissipation. So, all these 3 limitations are there even for the transistor. So, the transistor, final transistor limitation can come about. Okay. So, I naught is going to be therefore fixed by all these factors, and the minimum of these will be the permissible maximum current in the given circuit. Okay. Now, Vi, we know that we have to have the circuit operating for certain I naught maximum, that we know. Okay. Now, what is the range up to which Vi can be changed, or Vi is permitted to change? This is another important thing. This particular thing is very important because after you do this design and come up with Vi max and all Vi minimum etc., and then you start meddling with the circuit again, these things will again change. You will start meddling with the circuit particularly to provide protection for the circuit. At that point of time you should not forget about these limitations, and again these limitations will now change once all this protection circuitry come into picture, that we will discuss separately. Okay. Now, without the protection circuitry coming into picture, we know that Vi can keep on increasing now by itself. How much can Vi increase? One. Without going into power dissipation. With power dissipation we have come up with a Vi max. Have you understood that? And there you have to also perhaps bother about V naught minimum in a variable voltage regulator, right. That Vi max is known. Okay. Power is not at all demanded. What I am saying is it is not loaded. Now I am changing Vi. Breakdown. What is going to break down? Okay. Now obviously, okay, the collector base voltage will keep on increasing. This voltage is remaining constant. What is it? It is V naught plus V gamma. Okay. And this voltage is going on increasing. This collector base breakdown voltage is the limitation on that. Now that is as far as that output transistor is concerned, but other transistors might be now having more problem than this in terms of breakdown voltage. You have to see therefore all the transistors and see what the collector to base voltage of all these transistors. The lowermost transistor is the one which will most probably carry, likely to carry, right, the highest voltage in a given situation if it is connected to the input. If it is not connected to the input, you do not have to bother. For example, these particularly here, okay, this potential can keep on increasing, and this base potential is less than the output potential by R1 by R1 plus R2. So this collector base potential is definitely greater than the collector base potential of this. Understood this?
So that potential is the output with V gamma.
Which one?
It's always constant.
Which one?
That point.
This point, right.
Constant.
No, that is, suppose you are now changing V naught itself. See, as far as this is concerned, right, you are not bothered about it now because V naught itself is, let us say, very high, because V naught is V reference into 1 plus R2 over R1, corresponding to which Vi has to be still higher. Okay. So you have to worry about that Vi max which comes about due to that, not when this is at a certain V naught. That is why I am saying here as far as this transistor is concerned, it is only Vi minus V naught differential that matters. Okay. That will be always less than Vi, whereas other transistors are there wherein collector base potential can be higher and they might break down. So the breakdown voltage of these transistors, now you come to this point. Just this may be a trivial situation. This is Vz. The current in this is going on increasing. This is Vi minus Vz by Rs. There is a limitation, maximum current limitation on the Zener because of its power dissipation etc. There is a maximum current limitation on the Zener that might exceed. That will give you another value for Vi max. Understood? So you have to be very, very careful in your design. At all points you have to see, if I increase this voltage, is there any device that is going to break down? Okay.
So the bottom transistor always have the collector voltage is anyway it will be less than V reference.
Which one?
Bottom.
This one.
No, the bottom transistor.
This one. This one, okay, is not a problem at all. Here there is, it is this transistor alone, okay, which will have. And this you have to identify because we do not know how the transistors, various transistors are connected, okay. So you have to identify. Actually this is always at V gamma less than this, okay, and this is always at V reference, okay. And if you are having output voltage always greater than V reference, what is possible in this scheme, it is this transistor which is always having problem, not even this transistor, right. Is this clear? So, you have to therefore evaluate all the limitations due to breakdown, power dissipation and the basic maximum of current etc., which is occurring in various devices before you conclude which is the final thing that limits V I. What is it that limits I naught? Okay. Now that we have understood something about the limitations, okay. Given a circuit, you can find out the limitations, or given the limiting values, you can design a circuit. Okay. This is left to the designer concern, but you should be totally aware of all these limitations. Next, we have to protect. Now, why protection? Protection is only when protection comes into picture if you have not understood the circuit. If you understood the circuit, right, there is no need for any protection, but we cannot guarantee that everybody who is using this circuit has understood the circuit. Okay. So, protection is an important part of all the circuits dealing with high power. Okay. Basically, we have some ICs and then the discrete transistors attached to this, which are really carrying the high current. Okay. And it is these discrete transistors which you would like to protect, because they are the costly elements now. The IC may be pretty cheap. Okay. So, when it involves large amount of current drawn etc., we would like to have I naught versus, right, that is not I naught, V naught versus I naught absolutely constant at V reference into 1 plus naught. But obviously, because of all the limitations that are occurring, we would like to limit the current to a specific value, right. This in a given design might be coming about because of the following factor, maybe because of power dissipation, okay, maybe because of the current itself, okay, getting limited. So, this you have to investigate and see. So, there is obviously a maximum current which you are letting it to be permitted to flow through the output transistor here. So, the maximum dissipation in the IC, where is it concentrated? Output, because okay, all these things are carrying very small amount of current, negligible. This is the only one which is carrying the highest current in this circuit. Okay. So, basically it is the output transistor, okay, which has to be protected. How do you protect it? Why should it be protected? Mainly because as I go on connecting higher load or lower resistance to this, okay, this is delivering that current. Assuming that the design is properly done here, okay, that means there is no question of this comparator misbehaving, okay, the current division is still allowed. In such a situation, this current is going on increasing and power is going on increasing. Because of that, there is a limitation. I want to therefore not permit such a higher current flow. How should I do it? So, one way to do it is convert this is nothing but a voltage source now. That is why irrespective of the load, output voltage is remaining constant. At this point of time, I would like to convert it into a current source. That is the protection. Right? The moment current is trying to exceed a certain value, I do not want this circuit to behave as a voltage regulator. Purposely, I am preventing it from acting as a voltage regulator, because I know that this is a damaging current that is likely to flow, okay, and therefore, more than this current, if it is flowing through this, it will damage this. I will convert this whole thing into a current source. So, current sense is done. These are terminals for sensing the current. How do you sense a current? The current can be sensed always by using a series resistance. So, I am now using this series resistance to protect, but actually if I want to limit the current, I can as well put a series resistance, but that is a bad way of doing it. That is, I do not have to worry anything about the whole thing. I want to protect this transistor, right. So, I will put a series resistance here and then connect the load, but that immediately degenerates the performance of the voltage regulator, because series output resistance is increased, right. So, you cannot put a series resistance in order to protect the transistor. You can only put a series resistance low enough only to sense the current through the load. So, the load is now put here, and this is the R short circuit, we will call it. Okay. Actually, I am not shorting. This resistance, okay, is supposed to sense the overload current. Okay. Now, this is sensing the load current in this, because it is coming in series. Forget about the transistor for the time being. So, the voltage across this is I naught into RSC. That is going on increasing. So, if I am told that if this voltage increase above a certain value, okay, you divert the traffic. Traffic is this mount road. This is the mount road, right, main, okay, high current. The only way to prevent traffic jam is to divert the traffic. Why is it that the mount road is having traffic jam problem? Because there are feeder roads, okay, coming into the mount road. This feeder is coming from this, right. So, I divert the traffic here, okay, to another road, bypass road. So, I divert the traffic here. So, this is deprived of further excess traffic, and therefore, there will be constant traffic here. That high traffic which is permitted to flow through mount road will now flow. So, this is the sense resistor which will tell you when exactly you have to start the diversion. Okay. So, this voltage, the moment it becomes equal to, this is done electronically, V gamma, this is the police fellow, right. So, the instruction is very clear, right. The moment this becomes equal to V gamma, this is forward biased, this is already reverse biased. Okay. So, this transistor comes into the active region. Until that time we have told him you can sleep. The moment the traffic jam is likely to occur, right, you become awake and open the bypass road. So, this is the bypass road where the excess traffic is now flowing, right. So, you can see that this scheme, if I just draw it separately, we will understand it better. You have, this is the original transistor, and this current is going on increasing. So, I sense this current, please understand this, I sense this current using RSC, right, and then I obtain this as a voltage, this current is sensed and obtained as a voltage, and then it is again converted back to current, very sensitive, because this voltage, even if it changes slightly, there will be more opening of this, okay, and more of this traffic is diverted here. So, that is what? Negative feedback. Okay. Originally, the traffic was only flowing through this, right. This was not coming into picture. If I was flowing, I into beta was flowing here, that was the traffic. Now, if I is flowing here, what will flow here? What is the circuit? If you look at it, do you recollect this circuit? Huh? Huh? Whittler current source, right? With current feedback. Okay. So, there is now exact relationship between this current and this current. Okay. So, this current is now going to be limited to, it is a current source now, dependent only on this, and these are following one another exactly. And what is the current in this? V gamma by RS. Okay. So, this is changed over to a current source now. That means, if I connect a load resistance value here, which is lower than V gamma, what is it? If I connect a load resistance value which is lower than V naught divided by V gamma divided by RSC, that is the lowest resistance it can tolerate. If I put a lower resistance than that, current flowing through that load resistance is going to be now V gamma by RSC, right. So, this kind of limitation is now going to protect your circuit. Now, that is explained here graphically. This is the region where it is voltage regulator, and here you can sustain any output voltage. It is no longer voltage regulator, it is a current source of V gamma divided by RSC, constant current. Okay. So, this is the way we can protect. This transistor is within this device itself. Okay. Now, one last point before we close. This is not a good way of protecting the circuit. Why? Yeah. You look at it, as I already told you earlier, the PD max is governed by Vi minus V naught into I naught max. Okay. Maximum current is flowing, but V naught can be anything now starting from this value down to 0. Let us say it is real short circuit, RL is real short circuit. That means V naught is 0. Then the entire input power is getting dissipated in the IC. Now, this will give you another Vi max, right, which may be pretty low, and it is futile to design a circuit for this Vi max which may not occur, right. Vi minus V naught may be pretty low, and therefore, if I design this circuit only for this Vi max, it is going to be not efficient design. Okay. So, this kind of scheme has to be modified. What is the use of converting it to a current source? That is no earthly use, right. You convert into anything as long as, right, you are protecting the transistor. It is not necessary that you should convert it into a current source. So, depending upon what V naught is likely to be, right, I would like to therefore convert it into something which is not at all a current source. That this is Foldback short circuit protection, right, because after this load resistance is connected, for all the lower values of load resistances, it need not be a constant current. That means I have to sense the output voltage also, apart from output current, right. If the output voltage becomes different from this, then I need not sustain that constant current through the resistor. Okay. So, we will discuss in the next class this Foldback short circuit protection, which is the one that is to be recommended in regulators which are going to be remotely located, where if a short circuit occurs, I do not come to know immediately, right, and poor regulator might by that time conk out, right. So, this kind of thing particularly becomes necessary for the remote locations, where until somebody comes and repairs it, okay, it should be in this mode.